All right, thank you. So good afternoon, everybody. We're gonna get started with our final session of this ISER that's gonna be held in this room at least. And so this is the planning and control session, session 9, and we're running a few minutes late. We'd like to begin with a remote speaker, Jin Wook Hua. Are you on?
I should connect then.
One moment, we're gonna connect.
Yeah, just.
Do you need to? Okay.
Yeah.
Great.
Okay, sure.
Thank you. Oh, thank you.
I need to.
Appreciate that.
Yeah, I have to
I wasn't sure.
to get the
Link.
the link. Yes, of course. I think it's here. Yes. Has everybody got their own copy of the book? If you have anyone, I think there might be. I ordered 30 copies. I think we should be 27. But Usama and I don't need one. So if for any reason you have any colleague that you want to bring a copy to, okay. Yeah, I think.
There's an extra copy sitting up here near the projector. You can come grab it if you like.
Can someone admit me to the Zoom? Okay. Sure. Here we are, I think.
All right, Jin Wook, can you hear us?
Hi. Yes, I
Perfect.
can hear you. Can you hear me?
Yeah, we can hear you great. Can you screen
Okay,
share?
good.
You can start
I will share the
sharing your screen.
screen.
Sorry for the delay.
No problem. Oh. Sorry, this is a security issue. I mean, like, this is my. I need to give permission to Zoom to sharing the screen. Sorry. Yeah, it doesn't take
Okay.
any time.
Yep.
Okay. And then I will share the screen. Share.
All right, we can
Can you
see
share
it.
my screen?
Yes.
Okay, cool. And then I will make a full screen. See, can you see my screen?
Works fine.
Perfect.
Okay, good. Yeah. So, hello everyone. Yeah, my name is Jinuk, and I'm a research scientist from Samsung AI Center New York. Today, I present learning to generative cost-to-go functions for efficient motion planning. There are many efficient motion planning, such as there are many efficient motion planning, such as sampling-based planner. But this traditional motion planner has a problem, such as it requires to run from scratch for every new workspace. So they have some difficulty because, for example, in this kind of the example, they requires a lot of collision checks in cluttered environment or considerable iterative propagation of cost-to-go values. So we are interested in learning from motion planner in order to develop a continuous motion planner based on deep neural network. So we present C2G hub. C2G hub is a higher order function network. Higher order function network is a network that can generate parameters of another network. So C2G hub can learn from existing motion planners, and it can generate a smooth and continuous cost-to-go function networks over the entire computation space from the 3D workspace. So actually, we keep updating our C2G hub. So we have another updated version that is a little different from the Iser versions. ISAR version. Yes. So in ISAR version, the network architecture consists of three components. The first one is C-space mapping network. This C-space mapping network inputs the workspace, the images, and then output is a C-space map. C-space map is a kind of the cost value of the collision in configuration space. And then we input this C-space map and goal configuration into the C2G generating hub. And C2G generating hub outputs the parameters. And these parameters is used for reconstruction of the C2G network. And this C2G network can estimate predict the cost value to the goal configuration from any configurations. So with this C2G network, we can generate a trajectory because C2G network can estimate cost goal values to the goal configuration. We can just follow the gradient of the cost to goal value in order to reach the goal configuration. However, this Iser version has some limitation because of this C-space mapping network. We can apply this C2G hub for only 2D or 3D degree of freedom manipulators. So we updated this C2G hub, and now the C2G hub has only two components, C2G generating hub and C2G network. We input the point cloud into the C2G generating hub directly, and then C2G generating hub output the parameters of the C2G network. And C2G network can estimate cost to goal value between these two configurations. So we can generate ground truth from traditional planners such as Dijkstra or some sampling-based planners, and we can compute the mean squared errors between the predicted cost and ground truth. And the parameters of the C2G network is output of the C2G network. So we can backpropagate of this mean squared error to the C2G generating hub, and the C2G generating hub is trained to output the parameters of the C2G network. Let me explain more detailed network architectures. So C2G, we use the point net for C2G generating hub, since we input point cloud into the C2G generating hub. And also we can input top-down view images in the workspace, and we can also input the 3D voxel data into the C2G generating hub. In this case, we can use the 2D convolution neural network or 3D convolution neural networks. And C2G generating hub outputs the parameters of the C2G network. In this paper, we use the radial basis function network for C2G network. So these parameters is reshaped for C2G radial basis function network. And this C2G network can predict the cost to go value between the two configurations. Once we trained this C2G network from the sensor data, we can generate the cost to go function network. And as I explained, we can just follow the gradient of the cost to go value, and we can generate a trajectory. Let me explain more detail about the trajectory generations. So as I explained, we can generate trajectory by following the gradient of cost to go function from initial configuration to the goal configuration. So in this example, we fix the goal configuration. Goal configuration is this followed up point, and then we perturb the other one in the direction of the gradient with respect to the current input configurations. Once we generate the trajectory in the C space, it can have the motion as you show in these videos in workspace. So the key problem is in this trajectory generation, we need to compute the gradient. So one of the easiest way is we can just use a sampling method. We can just generate a sample around the current input configuration and then find the sample which has the minimum cost value. And also, another idea is we can use the gradient of the C2G network directly. This is more efficient and more faster. And let me show some result. This is a result with the 2D link. From this top-down view image, we can predict the cost to go value as you can see in these figures. In this example, the goal configuration is this blue dot point, and this ground truth is generated by Dijkstra. As you can see from these images, predicted cost to go value is very similar to the ground truth. And then as I explained in the previous slide, we can generate trajectory just following the gradient of this cost to go values. So we tested the trajectory generation with a simple 2D link manipulator. And then in the 3D manipulator, we input the 3D voxel data into the network, and then we generate to predict the cost to go value in the configuration space in these figures. And then this result is very similar to the ground truth. We also tested Shift-Hop with the 7-dimensional manipulator. In this example, we intentionally placed the end effector in the narrow passage between the obstacles. And also it requires flipping of the end effector. And then also it needs to rotate the base joint over the obstacles. The average computational time for planning is only takes less than 200 milliseconds. And one of the good point is in this Shift-Hop is it takes only 2 milliseconds to generate the parameters of the cost to go functions. So in the new environment, we can easily generate trajectory, and then trajectory time is almost to real times. So based on the comparison result, Shift-Hop is able to generate a feasible and near optimal motion trajectory within the 200 milliseconds. And we can say Shift-Hop is an efficient and practical method learned from existing planners. So the contribution of this paper is we suggest the Shift-Hop frameworks, and then this Shift-Hop can generate a continuous cost to go maps directly from the workspace without any discretization or considerable iterative propagation of cost values. And it can generate a smooth and efficient path. And also it is significantly faster than traditional approaches. And also we suggest a framework of the Shift-Hop. So we can apply, and then one of the, I want to say Shift-Hop is a framework learns any cost to go value in any space. So for example, we can apply this Shift-Hop for non-holonomic systems. So in non-holonomic systems, it has a different types of the cost values. So as you can see from these videos, even though it has a non-holonomic constraint, it can generate, Shift-Hop can generate trajectory with satisfying non-holonomic constraint and avoiding the obstacles. And also we are extending this Shift-Hop pick and place task from the point cloud, from the camera sensors. And then we are using this Shift-Hop pick and place task. Before I wrap up my presentation, I want to say one more things. We are actively, I'm from the Samsung AI Center New York. Yeah, we are actively hiring now. So if you are interested in our center for research scientist or research engineer position, please contact me or our center. Thank you for your attention.
Thank you, Jinwook. Are there questions from the audience?
Thank you much for the very nice talk. That's very impressive work. I was wondering,
Thank you.
If there were any, what were like the failure modes that you observed in this whole pipeline? Did you have any weird edge cases that you ran into that would require further attention, or did this work for most of the cases you tested?
Yeah, good questions, because I only shared actually the success case. Yeah, but one of the problem is because this Shift-Hop learns cost to go maps and cost to go functions, but it is not 100% perfect because it is a learning approach. So if you look at some cases, it is in this part has a slightly different. So sometimes, I mean, a Dijkstra algorithm doesn't have any local minima, but in my trained model, sometimes it has just some local minima cost values. So sometimes trajectory generation stuck in that point. So in that case, I'm trying to avoid the kind of the local minima case, but still struggling about that point. But the success rate is around 98% in order to for the generating trajectory. So I can say it is one efficient method.
Thank you very
Thank
much.
you.
Other questions? Usama?
Well, thank you for this nice presentation and ideas. I think the free space motion is still a problem, and especially when we go to higher dimension and more complicated environment, where the robot, multiple link of the robot are moving inside enclosures and different things of that sort. So, I mean, I think their community is not really building on works that came in different areas of this problem. And one of the areas I really think is important is the homotopic modification of trajectories through the mechanisms of elastic planning. And this is something that might really bring a lot of support to taking a plan and then modifying that plan in real time as a function of the sensory information. So I think ideas like this might really bring a lot of reduction in computation while avoiding many of the recomputation when we introduce new obstacles, new tools, and different things. So what do you think?
Yeah, it's a very good question. So because we are also interested in the kind of the change the environment or new environment, how to adapt kind of the change of the environment on real time. Right now, I'm in my case in this work is I planned in the static environment, and also I'm trying to generate a trajectory from the scratch as soon as possible. Mm-hmm. But as you said, kind of the elastic algorithm or some kind of the real-time sensing information is very helpful. Yeah, but yeah, I don't have any ideas right now how to change the post format based on the real-time sensor data. Yeah, but it is a very good point.
Yeah, I'm sure there are ways. So still, there is a lot of work to be done. Thank you very much.
Yeah.
Thank you.
Thank you.
Thanks again. Next up is Cosmo Della Santina, using nonlinear normal modes for execution of efficient cyclic motions in articulated soft robots.
Here we go.
Switch.
Yeah, that was not the expected
no.
outcome.
Maybe just put it into that without the casing. It works. No, you're good.
Okay, I'm good. Okay, thank you. So I forgot my pointer upstairs, so I will go back and forth a bit. But okay, hello again. This is another work together, another set of people. Some of them you may know. It's been mostly done at DLR. Okay, so main motivation, as many of the works that we do as roboticists, is nature, and especially here we deal with cyclic motion. So what we are inspired about is the capability of animal to perform a naturally periodic motion in a very efficient and effective and robust way. And a core intuition here is that behind all this capability, a key element is the presence of elastic terms. I mean, you can see on the right the usual spring mass system, which help us build intuition on a linear level, but there are a lot of studies on biomechanics kind of backing up this intuition. And this is indeed, again, one of the reasons why we started putting elastic element into our robots, leading to soft robots. Yesterday I discussed a bit about continuum robots. Today I will talk more about articulated soft robots or elastic joint robots. But in general, these are systems a bit more inspired by vertebrate animals. So we have kind of a rigid skeleton, but then we have elasticity and softness on the tendons and joints level. So, but if you take a mechanical system, you start adding some springs and you just let it evolve. This is what you get, most usually than not. So you start with some expectation for the natural world that everything is going to like evolve in open loop or whatever, but then what you get is most often than not this chaos, even for very, very simple system. It's just an open loop evolution of a double soft pendulum, so a simpler model of a walker. So what we are doing in the past few years, together with Aline, mostly Aline Albushaffer, is to introduce this framework that we are calling controlling eigenmanifolds. And in a nutshell, the idea is to go from the standard behavior that we find in nonlinear elastic system, which is pseudo-chaotic behavior, to recover some regularity. And there is an arrow here. And the goal of specifically this work of this Iser 2020 are two within this framework is to provide a first experimental validation, because so far it's been a quite like theoretical thing, and the other is to understand if some closed loop control that we had in mind could actually be useful in the practice, because I will give some more detail later. But before introducing the stuff that are really related to the paper, I have to, as quickly as possible, as already 3 minutes are past, introduce some background on this framework. And this is laid down by these 3 papers, and behind these QR codes there are talks that I've given where you can know more about this paper. They're all on my YouTube page, so you can just look there if you want. But really, really fast. So this is in two steps. The first step is to try to understand what the robot, the soft robot, can do well. And the way in which we do that is we extend. I mean, in linear system, I showed you before, there is this linear analysis that allows us to build all this intuition and the linear model analysis. And what you have is that you can take a linear system and you can identify infinite collection of regular oscillation that the mechanical system can execute in open loop. And you can put all of them together you end up with a surface. It's a planar surface, and it's called eigenspace. You may have heard about it. But if you go from the simple linear system to the nonlinear domain, or non-Euclidean, more specifically domain, the state space bends, and as a consequence, the eigenspace bend in what we call eigenmanifold. But this is again, from an intuitive point of view, is very much the same thing. So it's an infinite collection of periodic orbits, but these times they are not organized in a flat surface. Probably the most important thing is that we are developing behind all the theory and stuff. Right now we are evaluating these manifolds by hand, but we will release hopefully soon a toolbox for extracting automatically this structure for a given description of a linear mechanical system. It is just to give you a flavor of how these eigenmanifolds look like. So you have, for example, this is a double pendulum with some elasticity here. And for each energy level, you are going to have a different nonlinear oscillation, and this is just for one of the eigenmanifold 3 sections of the eigenmanifold. So these are open loop oscillation of the system. And these are instead for a KUKA lightweight robot. If you, just for fun, you just add some springs in parallel and you let it evolve in open loop. These are just a section of each of the 7 eigenmanifolds that this KUKA robot has, and for a given energy level. It's not super clear, very black, but I hope you can kind of figure out something from it. So I will speed up now. Once you have a description of what the robot can do, you can try to think of designing closed-loop controller to help the robot express its capabilities rather than forcing some behavior from outside. And you can do that with feedback control. We do that with two kind of a hierarchical closed-loop thinking. The first part is eigenmanifold stabilization. The idea is very simple. If you are outside an eigenmanifold, the behavior is messy. If you are on the eigenmanifold, the behavior is nice. So let's just select one eigenmanifold and let's make it an attractor of the system by means of feedback control. And it comes out that already a kind of a PD-like, simple PD-like action works. And this is nice. The problem starts with the other part, which is the energy regulator. So intuitively, you can label each of these oscillations with a different energy level, at least close enough to the equilibrium. And it's just a mess. So how you can regulate this energy without ever leaving the eigenmanifold, which is the important thing. And yeah, I guess no one of you really want to go into details here. But this comes the second part of the Iser paper, which is to try to test a bit more simpler controller that in theory it's super hard to prove, but in practice our intuition tells us that should work. And then they say, okay, let's first test it, and then we will try to prove it. And it's just a very simple bang-bang action. So the idea is that you have to compute a certain generalization of the energy of the system, and if you are above the desired energy, you just remove a constant amount, and if you are below, yeah, this should be actually on the other way around, but yeah, if you are below, you inject energy, so it's a kind of bang-bang controller, and that's, yeah. Okay, so a lot of theory, but again, we are in experimental robotics, so let's try to see how this works to give some reality check. And in the Iser paper, we focused on a segmented leg. So it is kind of inspired by a small dog, and this you can see overlapped the kinematics where the springs are, and this is the evolution recorded for an open loop evolution. And yeah, you can extract the modes. Again, this is kind of how the mode look like, quite non-flat surface, and this is how the acceleration field look like projected on the eigenmanifold, and this is just one of the modal evolution, how it looks like projected in configuration space. So this is how the whole thing works in simulation, which is always easier, at least, maybe not easy, but easier, but I think it's nice to show what happens after a few seconds. This is converged to a steady state, but the nice thing is that this is the control action, and the steady state has almost zero injection of torques of energy or whatever, because again, this is an open loop evolution of the system if you don't have dissipation. But so you end up with this hyper efficient oscillation in the end, and something bad is happening. Okay. Okay, it recovered, incredible. So, and this is what, if you now go with on the experimental side, we do the same thing, and this is the same controller, and with the actual leg, and these are the oscillation you have in for a few second injection of energy, and then it's this steady state oscillation. And you can do that for different energy levels. These are just some others, and this is how the actual oscillations are super repeatable, and they are quite close to the idea.
So you have an under-actuated system?
No. We can discuss about that later, but no, that's right now, no. I mean, the real system is under-actuated, but the model is not. But the nice thing here is that when you do a lot of theory and you have a lot of like non-linear control stuff, you most often than not end up with something that then it's super robust, but then this is how the whole thing behaves. So it's quite robust. And the intuition is that here we are just stabilizing the natural behavior of the system. And another nice thing is that if you play a bit with the mechanical parameter, you start seeing, without changing anything, some simple locomotion pattern arise. So it's something that came out during the experimental investigation for this paper. It was not expected. And then now we have recently, together with a PhD student from DLR, we have recently tried to make it a bit more formal. It's submitted to this ACC conference this year. So it's like this excitation of modes in this hybrid setting. And this is some very preliminary. No, this is not what I want to show. Yeah, very preliminary experiments with a quadruped. The soft quadruped is made of four legs. 4 legs of the one that I showed you before. Yeah. Last but not least, these are not for locomotion, but these are some of the modes that I showed you before in simulation, and these are on actual KUKA robot. We are simulating, we are not adding in parallel any spring, which is not possible, but we are simulating the presence of the spring. But all the rest is just excitation of these natural behaviors. And that's all. Thank you very much.
Are there questions? Yes, go for it.
Thank you very much for this very, very nice presentation. So if I understood well, so the control is based on the energy of the system. And my question is it possible that for a specific system, it is not, we don't have an accurate estimation of the energy, and if we have error on the estimation, can we still apply this type of control in your intuition?
Yeah, so the interesting thing, so I also want to clarify that the bang-bang control way to do things was used in this Iser paper, but this more recent one are based on a more continuum loop, still very difficult to prove. But yeah, I mean, in all these systems, you have a kind of first order intuition about which is the energy, but you have a lot of uncertainties. I mean, maybe in the KUKA robot a bit less, but with this like more real. Okay, I mean these are robots that we have built ourselves at DLR, so it's. A lot of linear identification goes into understanding the exact parameters, but not only the energy, but the eigenmanifold itself are very, of course, they are very model-based. But at the same time, what we are doing here, again, is not forcing some external behavior. It's just some injecting a bit of energy when it's needed and pushing the robot away from some like chaotic area, and then we see that it's actually much more easy to make it work in the practice rather than to prove than that things works in the theory.
This is so nice. I spent a lot of time talking with Aline about this and still don't understand everything.
Us neither.
So, but to reassure you, there is no problem if you take a holonomic multi-link robot. The energy of the system is the sum of potential energy and kinetic energy. And if you use just a PD controller, the proportional part is going to be added to the potential energy. And that keeps the system conservative. And the damping, if it's done correctly, will just take out energy and you have no problem whatsoever. I think here we are talking about systems that where energy is injected and removed, and you have all kind of other phenomenon that comes. But for most robots that we're working on, don't worry, there is no problems of that kind of challenges. But this is a wonderful problem to look at. Thank you for doing that. Sorry, it was more a comment.
We're out of time for questions. Thank you, Kazuma. Sharon is up next with Rapid. Thank you.
I do need the audio.
And this one, this presentation uses the computer audio.
Yes.
Here you go. You're not on the other screen.
Okay, I'll see. All right. Hi, everyone. My name is Sharan Nayak. I'm a PhD student at the University of Maryland, College Park. And today I'm going to talk about RAPID, which is an algorithm for performing quick replanning under change dynamical constraints. And my advisor is Dr. Michael Oti. So there are many situations where the dynamical constraints of a vehicle may change mid-mission, either due to damage to the vehicle, or the vehicle may undergo a change in its mass and shift in its center of gravity, and because of that, it may undergo a change in the dynamics. So in that case, the vehicle may quickly need to come back to the base location for repair or safety, and do so while avoiding the obstacles and also avoiding people in the environment. So to do this, there's a need for a quick replanning algorithm for the robot to quickly come back to the base location. So to this effect, we present an algorithm called RAPID, and RAPID stands for Rapid Planning for Interchange Dynamics. And RAPID is applied in the domain of sampling-based motion planning. So to understand how RAPID works, consider this picture to your right, where you have a quad rotor at the base location, and you have a package at the top. The quad rotor has to use its nominal trajectories, which are given in green, and it has to find a path from the base to the package location. So to do so, it might use a sampling-based motion planning algorithm, something like RRT, which is a rapidly exploring random tree, to build the motion tree up, and then through the motion tree, find a path from the base to the package location. Next, the quad rotor is going to pick up this package, but due to the asymmetrical weight distribution in the package, the quad rotor will experience a change in its mass and a shift in its center of gravity. And because of this, the trajectories that the quad rotor execute will change from its nominal trajectories to the altered trajectories, which are given in pink here. So the question that we were going to ask is, instead of replanning from scratch using RRT with the new trajectories, can we use the information that is present in the original search tree to speed up the replanning process so that it quickly comes back to the base location while avoiding the obstacles? So that's what the RAPID algorithm does. It uses the heuristic information that is stored in the original search tree to speed up the replanning process, and then find a path from the replan start to the base location. So in the next few slides, I'm going to go over the RAPID algorithm. So this is the pseudocode for the algorithm. Due to time constraints, I'm not going to go over every line in the algorithm, but I'm going to explain two important steps. The first one is the nodes insertion. So to understand nodes insertion, consider this picture to your right, where you have the original search tree that was built from the base location to the replan start location. And then you have a partially built rapid tree, which is given in pink here. And focus your attention on the node which is designated as X current. So the nodes insertion step involves selecting X current as the center of a ball of radius delta X. And within that ball, we select all forward tree nodes, and we push that into a priority queue. So while pushing to the priority queue, the cost function that we are going to use is given by this expression here, where g of x current is the cost from SAT, h of x is the cost to the base location, and d of x current x is the distance between the x current location and h of x, or x, which is the node in the forward tree. And it doesn't have to be Euclidean distance. It could be any distance that is defined in the configuration space of the robot. So that was the nodes insertion step. The next step we are going to have is the propagation step. So for the propagation step, what we do is we first pop out the best node that is currently in the priority queue, and the best node is selected as the one that gives the best value in the cost function that was defined in the previous slide. Okay, so the best node, that is designated as X destination. So that's a node in the forward search tree or the original search tree. Next, we select a node in the partially built rapid tree, which is designated as X source. And that is the closest node to X destination in the forwards or the original search tree. Next, we search for a trajectory that starts at X source and gets as close to X destination as possible. It's not possible that we can connect X source and X destination because in our work, we assume that the two-point boundary value problem cannot be solved. So we can only hope for a trajectory whose endpoint gets as close to X destination as possible. Next, we set X new to X current. And if you remember from the previous slide, X current was the node where we selected that as the center, and then we selected a ball of radius delta X. So we set X new to X current. And that's the propagation step. So we again go back to the nodes insertion step, and then the propagation step, and we keep repeating this process until we reach the base location. And then we are able to find a path from the replan start to the base location. And it is important to remember that the new tree that was built is using the altered dynamics. And with the rapid tree, we are not replanning from scratch. We are using the information from the original search tree to speed up the replanning process. Okay, so that was the rapid algorithm. We'll now move on to the experiments. So to test the performance of rapid, we conducted both simulation experiments and hardware experiments. So first, I'm going to quickly go over the simulation experiments. For the simulation experiments, we used two vehicles. First one is the unicycle. And for that, the dynamics change was represented by a changed linear velocity from 6 meters to 3 meters per second. And the original and the altered trajectories are given at the bottom of the unicycle image. Next, we have the quadrotor vehicle. For that, the dynamics change was represented by a 10% increase in its mass and a shift in its center of gravity, with a 4 meter and a 1 meter shift in the XY parallel axes. And these are the original and the altered trajectories for the quadrotor. For the comparison with rapid, we used two algorithms. One is RRT, and the second one is SST. And for each RRT and XST, we use two combinations of RRT and SST. One is using the random propagation step. The other is using the extend propagation step. The number of scenarios that we use is 100, with each scenario having 3 trials. And the scenario is defined as a randomly selected base and a replan start location with a random number of obstacles in the configuration space. Next, in terms of the metrics, we use the algorithm completion time, the path length, and also the flight time for the hardware experiments. And the hardware experiments I'm going to talk about in a future slide. Okay, here we show a video of the simulation experiment that we conducted for the unicycle dynamics. On the left, we have the rapid algorithm. On the right, we have the RRT algorithm. So I'm going to run this video now. So you can see in both of these simulations, we originally use RRT, which is the green tree, to find a path from the base to the replan start location. And then we use rapid on the left and then RRT on the right to find a path back to the base location. I'm going to run this video again because it ran pretty fast. So you can see on the left, rapid was able to reach the base location faster than RRT on the right. And you can see the path length too. The path length was better when using rapid and then when using brute force replanning using RRT. So in terms of the software experiment results, we have 4 graphs here, 2 for the unicycle on the left, 2 for the quad rotors. The graph on the left represents for the computation time. The graph on the right, the second graph represents for the path length, and the same goes for the quad rotor vehicle. And on the x-axis, we have the number of obstacles. So we vary the number of obstacles in the environment, and the x-axis represents the number of obstacles that we currently use in an experiment. And in each of these graphs, smaller the value, better is the performance of the algorithm. And you can see that in all these graphs, the variance of rapid was able to perform better than the variance of RRT and SST. Okay, so that was the simulation experiments. We next move on to the hardware experiments. So for performing the hardware experiments, we set up a small obstacle course in our lab, which basically consisted of 4 obstacles. On the very left, you see the front view of the obstacle course. On the right, you see the top view. And the obstacles were modeled as circles for easy collision detection. So we are planning in 2D space here. And we also have an extended obstacle space that we put for safety margin to account for the non-zero vehicle size and also to account for drift in the quad rotor. To actually conduct the experiments, we used a modified Bebob2 quad rotor, which is fitted with the Intel upboard. And this was the board that we used to run all our algorithms on board. And here are some parameters related to the hardware experiments. Okay, so we set up the obstacle course. The next was to generate the trajectory libraries for the quad rotor. So for the original trajectories, what we did is, for each trajectory, we gave a position reference 1 meter away from the origin, or the initial position of the quad rotor, for 4 seconds in 10-degree increments. And we are using the nominal PD gains of the quad rotor. And the image that you're seeing here, or the video that you're seeing here, are the quad rotor executing these different trajectories. So for the altered trajectories, what we did is we followed the same process as when we generated the original trajectories, except that we changed the PD gains to 1/3 the nominal gains of the quad rotor. And the altered trajectories, the image is given to you right there. So we execute each trajectory 10 times and then calculate the mean of the trajectories to generate the trajectory that you see in the images for the original and the altered trajectories. Okay, so we set up the obstacle course. We generated the trajectory and the original and the altered trajectories. So the next step was to actually run the experiments. So we ran 10 trials of hardware experiments, and I'm going to show 1 trial here. So same as before, we'll have a rapid running on the left and RRT running on the right. So I'm going to run this video now. So we originally used the RRT algorithm to find a path from the base to the replan start location. And next, we use rapid on the left to find a path back from the replan start to the base location. And on the right, we are using brute force replanning using RRT. And RRT rapid is using the original tree information to speed up the replanning process. So you can see on the left, rapid was able to come back to the base location faster than when we used the RRT algorithm. So I'm going to quickly run the video again. So like I said before, we are using RRT algorithm, and we are executing the trajectories which are there in the trajectory library. And then we use rapid on the left and RRT on the right to come back to the base location. And you can see rapid was able to reach the base location faster than when using RRT. So that was the hardware experiment that we did, or one trial of it. So in terms of the hardware experiment results, like I said before, we performed 10 trials. And if you see the results, Rapid was able to perform better than RRT in terms of the average values for all the metrics that we considered. So in conclusion, in this presentation, I presented an algorithm called RAPID, which stands for Rapid Planning for Interchange Dynamics. And RAPID allows you to perform quick replanning under change dynamical constraints. In RAPID, what we do is we use the heuristic information that is stored in the original search tree to speed up the replanning process. And we conducted both simulation and hardware experiments to validate the performance of RAPID. So one final slide. In terms of future work, we want to test RAPID using complex systems, using non-zero velocity constraints, because in all the experiments that we did, we designed the trajectory so that the end velocities were zero. And this almost never happens in real life. So we have actually already done some work on it, but due to time constraints, I can't present that work today. But yeah, so next is we want to develop an asymptotically optimal version of RAPID, because in all of our experiments, we only ran RAPID until the initial solution was found. But we also want to find better and better solutions as time progresses and develop an asymptotically optimal version. And finally, we want to do some analysis on how much the dynamics will have to change before RAPID actually starts performing pretty bad. And using brute force replanning might be actually better. And these are my references. Thank you. Do you have any questions?
All right, we have time for one quick question. So does anyone have a question? Nobody? Yeah, go for it. And Sarah, maybe you could set up while that's happening.
Thanks.
Maybe this is a bit out of the scope, but have you thought about how you estimate the change dynamics when you pick up a package?
How to estimate the change dynamics? Yeah, that's a good question. So we have not looked into how to identify the change in dynamics, but I know there are like system identification methods using reinforcement learning, or there might be some other methods too. So that's one way of detecting the change in dynamics.
Okay, thank you.
Yep.
Let's thank our speaker again. All right, next up is Sarah Aguaviva Manzano with soft actuators and recurrent neural networks. I think you're good.
It does this annoying thing where I have to bring it over.
That's fine. I remember this AI too. I had the same type of slides. Here you go.
All right. My name is Sarah, and I am here to talk about high bandwidth nonlinear control of soft actuator using recursive network models. This work was done in collaboration with Patricia Coy, Rob Shepard, and our lab. And I am particularly interested in, my work is particularly interested in starting to bring advanced computation into the computers that already exist in the tiny platforms that we design, name it soft, small soft components. So kind of fully untethering the computation from a big central PC that's all powerful. So the too long didn't read about this project is that we managed to control a platform that looks like this, and I'm going to go into a little more detail, at 120 hertz by learning the forward kinematic. And this didn't require us more than 2.2 kilobytes of flash memory in a microcontroller that's very small. And we wanted to do a feedback controller because the group that designed this soft component was particularly interested in rejecting mechanical and electromagnetic disturbances. So the work that is prior to this and kind of the motivation for this problem is the design of optical lace sensors named at the time. They were rebranded to light lace sensors. And the technology consists of light guides that are threaded inside a soft mesh that is 3D printed. And these light guides are really stretchy, bendable, they're really flexible. And some of the light guides emit or transport light in the IR spectrum, whereas other light guides just have photodiodes connected to them just to sense the flicking of light as it gets deflected as we twist, bend, and extend these soft robots. And the thing about these sensors is that they are allowed to move within the structure, and they are organically shaped, laid out in the structure, meaning that someone did it by hand and kind of weaved within this soft mesh where these sensors are. And here is a video from the science paper where this was published by Artemis Shu. And I hope you can see the sensor readings, but as you twist, bend, and stretch this soft component, you find a nonlinear relationship between the sensor readings and the shape of this mesh. And we were interested to know if we could use these sensors for control of a platform like this. Originally, the platform was mounted like this. That's how it was recorded in this video, which had one servo that bent the surface, one servo that extended the surface, and another servo that twisted the surface. So there was a one-to-one relationship between bending, twisting, and stretching. So the control problem wasn't interesting at all because it was like, I didn't even have to implement a controller. So we decided to make the control problem a little bit more interesting by mounting this soft mesh in a cantilever setup. And we pull the end effector. We call this tip of the mesh the end effector. So we pull it using Kevlar threads and two high torque sensors. Two high torque servo motors. Yeah, these were our materials. And I'm gonna move on to the next slide. So we figured this was a good opportunity for learning the forward kinematic of this N effector based on the feedback of these sensors. We wanted to build a controller where the only thing observable from the robot was its own proprioception and not signals coming from the motion capture. So yeah, I mean, we figured it was a good opportunity for learning the patterns, exploiting the patterns of these sensor signals to do control. And these require us to collect about 9 hours of data. And to do that, we repeated some motions, some prescribed motions of the robot, namely a circular motion, up, down, and sideways, kind of like zigzag. And we repeated that like about 200 times. And what we recorded was the control inputs, meaning the servo like angles. We recorded the position of the N effector. And we also recorded the history of sensor readings. And we collected this at 120 hertz. And to learn the transition of outputs between one discrete time step and the other, we use particular layout of network model that was proposed in previous work by Don Soloway from NASA in 1996. He originally proposed having a neural network where you have, originally he proposed a single fully connected layer. You have your inputs, and your inputs of the neural network consist of a history, a short history of the past inputs, meaning motor settings, a short history of past predictions, and signals from internal signals that you can get. And there was a single layer. And you will get the output at time t, right, from t minus 1. And then to get like t plus 1, you would feed back the output from t. And this way you will like roll this DQ. I think I added the feature of the sensor signals because originally the controller was a single input, single output controller first. And second, it didn't use any feedback from sensors. So I added that in the feature space of the neural network. And I tested different layouts of this like heart network. So I call it the child network. And the reason is because it's a hierarchical network, if you think about it. Because it is recursively feeding back to itself, if you kind of exploit the neural network graph, it will be kind of like a tree. And this structure inside, we call it the child. And I was able to make this inside child structure have an arbitrary architecture using some numerical approximations. The person who originally did propose, the original work, did it by hand, and I also did it by hand as well, but it limited me to only fully connected layers. And I wanted to add, layers that had some memory in them. So I learned the forward kinematics, and I use, in this plot, you can see how a recurrent child structure kind of outperforms a fully connected child structure. So in red, you can see how the recurrent child structure kind of like captures these artifices within, the position, whereas like the fully connected one is only able to capture like the, the big, I guess like the higher level motion. And so to make this multiple input, multiple output controller, the first thing I had to do was to impose the first two terms of our cost function to be that of a multiple input, multiple output controller. So I introduced this weight matrix that allowed me to penalize different errors within the inputs and outputs. It is important to know that that y hat in the cost function constitute the neural network prediction. And the third term was a smoothness constraint term that was first proposed in the original work. And I anecdotally realized that it did impose like less jerky motion, so I left this term in the cost function. The control problem then originally was set up as the second derivative of the cost function with respect to the costing horizon times the difference in costing horizon equals the minus the first derivative. So the challenge here was to find the gradients of that model that we originally set up. Because of the chain rule, that will show up in our differentiation. And I managed to do that using second order finite differentiation stencil for those gradients, and I compared them against the automatic gradient from TensorFlow, and I was able to get small errors with the same input, so I consider that that was good enough for my gradients. So I solved this equation using a Newton-Raphson solver, and these are some results, the results we showed in the paper. So to your left, you see the path where this tiny computer thinks the n effector is based on the sensor signal readings. In the middle, you see the measure path, which is what we actually measured that the n effector was. And here is like kind of the motions that provided these results. Something that I would like to mention is that these results, I ran this experiment like over 50 times to show the results. And even though the sensor signals can like jump and have some noise to them, I was able to reproduce the same paths with the same accuracies over and over again, and this is just a sample run of the path following. So I was wondering if it was just a fluke and, like the neural network model was completely ignoring the sensor signals. So I decided to see if, the neural network would respond to weight disturbances, forces within the structure. And the reason why and it did, right? And here we put mass with magnets, and the magnets is because the requirement was that it was, we wanted to prove that the sensors are robust against electromagnetic disturbances, right? But what I cared more about was like the mechanical forces, right? And the controller corrected for that, but it is important to notice that I kept the same like saturation, but it did saturate when I was running that experiment. And I know I evangelize about these tiny computers. All right, so I like to put neural networks in microcontrollers. And I keep evangelizing about this, so it would be disingenuous of me to not run this controller in the microcontroller. So I did. I implemented a set of tools that allows me to do the same computation that I did in the higher level Python prototype into this tiny microcontroller. And here's the robot using only the sensors not plugged into a PC. This cable over here is just providing power to the motors. And thank you so much. 1 minute, right? Thank you so much.
Are there any questions for Sarah? Cosimo. I'll let you use mine.
Thank you. So yeah, very, very, very nice work. This is more out of a curiosity. You said that you had to collect like a very big data set where you have repeated many times the same actions. My question, it sounds a bit strange to me because I would expect that the same action would provide the same output, so there would be redundant information.
So there is. So we observe certain level of hysteresis in our system, and another thing is that because the block is bendy, after 9 hours, the material does fatigue. So we were dealing with that, that challenge too, right? In fact, one night, like this is an anecdote, right? But one night I left the block without any support, and it just like sunk. And I found it the next day, and like, what is this? I had to leave it in a surface. So yeah, like we were also dealing with that, and the reason why I collected data for such a long timeline is because we wanted to, if there were to be sensor drift, I wanted it to be robust against that. Yeah.
Let's thank Sarah again.
Thank you.
Oh, could we get these soon? Sure. Thank you. All right, is Burke on the line? Burke, are you with us? Okay, 1 second. Let's get the audio going here. Burke, can you say something again?
Hello, can you hear me?
Oh, great. We can hear you. Excellent. And we can see your presentation, so you're ready to go. Burke Callie is up with some manipulation planning work. Take it away.
Awesome. Thank you very much. So I'm Berk Charlie from Worcester Polytechnic Institute. Would love to be there, hopefully in Singapore then. So this work is in collaboration with Imperial College London, and I will talk about in-hand manipulation. So the in-hand manipulation problem that we are focusing on, of course, mostly about dexterous manipulation skills that helps humans and robots to prepare a grasp object and make it ready to use. And or we can also use the a grasp object using in-hand manipulation skills. So, for example, we pick a pen from the table, we slide it within our hand, maybe we rotate it a little bit, and then after we position it in our hand, we use our hand dexterity in order to utilize that pen. And of course, we try to avoid here the need for regrasping over and over again. And when we look at the literature, what we see here is that there's some vision-based manipulation work with underactuated hands. This was actually presented in Iser 2018 by our group when I was in Yale. And it was basically utilizing the compliance of these hands for contact stability and utilizing a vision-based manipulation framework. From University of Utah, we have a model-based technique via relaxed rigidity constraints. And they are also focusing on fine manipulation. And also there is this famous MIT Carnegie Mellon work on extrinsic dexterity, which mostly utilizes extrinsic constraints, so other objects in the environment, but also sometimes the hand-object dynamics in order to reposition the object within hand. However, when we look at all these medicine systems, what we see is that it is still very, very hard to achieve within-hand sliding in a controlled fashion, and also having large rotations with these hand-object systems. For example, this is a experiment that we were doing, trying to implement our vision-based control framework for controlled sliding, but we wouldn't be able to get repeatable results. So the controlled aspect of sliding was not really there for us. But it's a very, very essential part of within-hand manipulation. So how to achieve that? Or in our prior work, we then started looking into this idea of like variable friction surfaces. So there are basically two interlaced surfaces. One is a high friction surface, one is a low friction surface. So we can put one or the other as we want actively. So the object either slides or rotates on the surface. For example, here you see that the left finger is low friction. Therefore, the object slides within hand. And if by just like doing this kind of sliding motion, we can gate this object to the tip of the finger, or so this is a very repeatable control sliding. Or in this example, for example, the object will rotate 180 degrees, but still maintain its same position. So this is a switching system. This is a non-holonomic system, but it really allows us to stay within the quasi-static levels, quasi-static framework, and still achieve very consistent results for controlled sliding. So our previous work was on the mechanical design of this hand, and in this work, we were focusing mostly on the control and planning aspects. And more specifically, we talk about position and velocity kinematics of the hand. We present here a motion planner and apply it in a feed-forward manner. We present a visual surveying controller and its performance, and a hybrid control that basically combines this motion planner with visual surveying. We implemented 162 experiments with 5 different objects. So some assumptions and the scope of the paper here, we are only focusing on planar within-hand manipulation here. Our system can work with or without support plane. So all the experiments that we have done, they didn't use any support plane. So that's a good feature of the system. We assume that we know the geometric model of the object, but it doesn't have to be very accurate. And I will talk about it. And we assume that the target object has at least one flat surface, so it shouldn't be all round. For example, a circular object for us to achieve controlled sliding. So when we look into the planner, we use the A-star planner. And here, the plots that you have seen, so for reference, I added this picture here. This is the trajectory that the object follows in the image. And this green star here is the goal location, and the dot is the initial location. So what we basically have a weighted A-star algorithm. And here we have this epsilon factor. The reason that we edit there is that because once we do not have the epsilon set it to 1, of course we stick with the optimality criteria here with our optimistic distance measures, but more nodes are getting generated, and that is time taking. On the other hand, if we have set, for example, epsilon to 2, we enforce more greedy search, and that reduces the amount of nodes that are being generated, so makes the system much more faster to plan. We also have this beta gain here in our heuristic. Its main function is to encourage the system to stick with the previous action that it takes, because since this is a non-holonomic system, if it can basically, in order to follow a straight trajectory towards our goal, it basically switches back and forth, which is not a behavior that we would like to encourage due to the mechanics of this particular system. Instead, when we set, for example, this beta to some other values, we encourage much smoother behavior here. And our closed loop system, basically, it gets a very accurate positioning, but of course, due to non-homogeneity of the system, it tries to follow a linear trajectory in the image space. So that causes this kind of chattering that you see. Also, planning for rotation motions in this kind of visual surveying schemes is not really straightforward. So we were using some heuristics in order to achieve that. But in general, this closed-loop system, as expected, provides us a good amount of positioning accuracy. And we have a hybrid method, of course, joining the powers of these controllers together. So once we, for example, have a feed-forward planner, we have smooth trajectories, but as you can see right here, we cannot achieve our goal because we are implementing it in a feed-forward manner, but the execution is fast, the execution is smooth. On the other hand, we have very high accuracy with visual servo control, but it just doesn't provide us very smooth trajectories. And our hybrid method basically combines the best of both worlds, which is when the system deviates from the plan, the visual servoing controller kicks in and puts it back to its trajectory, and that allows us to stay in the trajectory and also remove some steady state errors. So if we see these systems in action, so feed-forward planner, as expected, provides us smooth trajectories, fast execution, but not really accurate. Has a lot of steady state error and trajectory following errors. On the other hand, the visual servoing algorithm here provides us really accurate positioning, but it is relatively slower in execution and does not provide us really smooth trajectories. When we combine both of these algorithms together, we both have the accuracy and medium fast execution. So it's not as fast as feed-forward planner, of course, but it still does a very good job killing the steady state error and giving us some smooth trajectories. In our experiments, we have used these 5 objects with different dimensions. And we did 162 experiments and 4 different poses. So the examples that I've shown were pure sliding examples, but we also, so that was only one of our goal poses here in our experiments. We had one of our goal poses, for example, required 180 degrees rotation of these objects for the cubic case, or basically changing 2 sides for a given object. Or some of them require one side change. So the rotation is always in the picture here. What we have seen was that the switching actions between low friction to high friction that causes that chattery motion, that is, of course, higher in visual servoing case. It is the lowest in the motion planner case. And when we look at the hybrid, it's somewhere in between. But the good part in combining these methods is having a good amount of accuracy while achieving some degree of smoothness and having some optimality in the path that is generated. We also did some experiments by introducing a 20% error in the object dimensions and feedback-based methods demonstrated a robust performance here in terms of maintaining the average error staying very close to the non-model error case. And finally, we extended this work in 2021 with our ICRA submission. So we extended this, we applied these methods to a region-based planning technique that we also were able to do some 3D within-hand manipulation by using extrinsic constraints. So other objects as well. One thing that we have noticed is that our ability to manipulate the surface friction helped us quite a bit while implementing these kind of extrinsic dexterity-based approaches as well. And we are working on various modifications of this hand, namely variable palm width and also basically implementing similar ideas to other finger structures as well. So yeah, that was the end of my presentation. Thank you.
Very nice. I mean, dexterous manipulation is a really, really difficult problem, and in hand manipulation, especially with the multi-fingers, is quite complicated. So using variable friction is a very good idea, I think. You mentioned 3D, and I was waiting to hear something about that. That it seems like you're exploring 3D, and that's very important. I was wondering if you're familiar with the roller-based manipulation. The roller-based, this is work that comes from Stanford, my colleague group, Ken Salisbury. And they are, I mean, basically we need to instrument more and more the hand. So there is this idea, and it seems to be performing very well. So I wanted to see what you think. Do you want to combine roller with the friction, etc., etc.?
Definitely, that's a very, indeed, there are, for example, some, I got to learn about the roller-based one very recently, so I will be checking details about that. There were some other examples of like conveyor belt like finger surfaces that was also very interesting, definitely. So making it actuated, like making this finger surfaces actuated is really a very powerful aspect here that we can explore. Yeah, I am actually wondering, so right now, to be honest, achieving this kind of low friction, high friction surfaces is not very, how to say, compact to implement, very easy to implement, but we will be basically looking into ideas of like maybe indeed like a combination of these two, like actuated versus, or maybe we can run a comparison. But yeah.
Great. Let's thank Burke again.
Thank you very much.
Thank you, Burke. Next, we're going to move on to Hamid Izzadininia, sorry. And he's going to be discussing non-prehensile motion. So you can take it away. We can see your slides just fine.
Okay, can you see my slide?
Yes, we can.
Okay, sorry. My name is Hamid Izzadinia, and today I'm going to talk about our paper, Non-Prehensile Riemannian Motion Predictive Control. So this is a joint work with Brian Boots and Stephen Seitz, and the work was done at University of Washington. If you look at industrial robots, there are a huge number of robots working in manufacturing lines where everything is pre-programmed and determined in advance, and robot working in a structured environment with fixed setup. And if we compare it with an unstructured environment, the problem becomes more challenging, as it needs physical interaction with an unstructured environment, where robot needs to interact with a variety of objects with different shapes and sizes and manipulate them in an efficient way. And this needs a cycle of perception and action and execution in real time. And it needs to be an efficient manner to do a kind of a task or like robotic task. And how we can do this? So we proposed learning 3D recomposition for robot manipulation. So this task of 3D recomposition is not a new task. And actually the first PhD thesis in contribution was about while Larry Roberts was about taking an image of a simple scene and processing the edge information in the image and recomposing the scene in 3D in such a way that we can view it from a novel viewpoint. Soon after, a project led by Patrick Winston and advised by Marvin Minsky in MIT lab, which was called Copy Demo, taking an image from a blocky world and processing the information of that blocky world and inferring what the affordances of the blocks, and then try to recompose the same scene using a robot manipulator in a closed loop manner. And they did this a long time ago. Our work is also related to recent efforts in deep robot learning and deploying 3D physics simulation environments for learning robotic policy. This spans from learning visuomotor policy, domain adaptation, to transfer policy learning simulation to the real world. But in contrast, we learn to generate the simulation environment by recomposing the 3D scene and incorporating simulation physics environment as a computational model to predicting the outcome of robot action trajectories in closed loop. So we propose non-prehensile Riemannian motion predictive control, where we have controllable objects and a goal location, and we want to, and there are some movable obstacles in the scene. We want to use the robot controller to push the object on the surface to the goal location. Maybe the obvious path for pushing an object to the goal location is just a straight line from the start to the end. But if you do that, we'll collide with other objects in the scene, which are the obstacles. And it also may kind of deviate the path of the object. Whereas we learn deserve controller, where we push the objects to, we learn the policy that can push the object around the obstacles and try to get the objects to the goal location without colliding with the other obstacles in the scene. We also tested that on the RC car road platform, where we push the goal objects to the goal location, and there are some movable objects, movable obstacles on the scene that we put on the ground. And we want to do the same with the mobile robot, like RC car here. So conventionally, planning algorithm has been used for solving non-prehensile manipulation by incorporating search techniques to create a trajectory of kinematic movements for a robot arm to push or rearrange objects by modeling the dynamics of a robot arm in contact with the environment. Well, our approach is more general, and the task we consider is more challenging as it involves multiple object interaction in the scene. So we use Riemannian motion policy, or in short, RMP, where we construct a tree out of the scene, and we have a root node and leaf node. The root node here is related to the configured space of the controllable objects, and the leaf nodes are related to the task subspaces. For example, for the obstacles, we have like the avoidance task subspace, and for the goal location, we have the attractor task subspace. And we also propose a real-to-scene located reward, where we take an image from the input scene and recompose the scene in simulation. So here we're using the RC car and the YCP objects. And then from that, we construct the RMP tree, where we have, for example, the bool. Here is the configurable space of bool is in the root, and other obstacles like banana, pitcher, cracker, box, and mogs are the obstacles, and the goal location is determined in the problem. Then we use that to compute the reward function. The reward function is computed based on the distance improvement of the goal object's movement toward the goal. And that is how much from t-1 to t we get closer to the goal. And we subtract that with the collision penalty, which is a summation of the distance caused from t-1 to t for the obstacles. So we want to have less motion of the obstacles and the better motion of the target objects, the goal location. Then we compute the reward for various simulated trajectory in that simulation and select the action for trajectory that produce maximum return based on the reward function that we have. And we have a decayed reward over the time for different trajectories. This is similar to applying MPC and the scene. So we compute different trajectory with different control parameter, and then take the best one and apply a single action in that trajectory, the first action in the robot, and then go to the next iteration. So we have this sort of closed loop control, where we take an image from the scene with the goal location and the target object. Then we recompose the scene into the simulation, the same scene simulation, and then using that reward function, look at reward function, we compute the best control parameter for the robot and apply one action in that trajectory and get to the new location for the robot and the target object and the other object in the scene. And then we recompose it again and compute the control parameter and apply it one action. And we do it in over the time and until we push the target object to the goal location. For example, in this example, you can see that the ball gets to the green dot, which is the goal location. For learning the recomposition part, we use 1 million synthetic scenes for with diverse arrangement of the object and goal location. For example, here for the robot arm, and we put the object in different location and capture that in the RGBD sensing, and then use that for training our recomposition part. We do the same thing for the RC car environment, where we generated again 1 million synthetic scene and learn our recomposition for this environment as well. So this is a result of learning that composition simulation and applied in the real scene. And these are the real objects from YCP. And you can see that even in the presence of very heavy occlusion and clutter for objects and different poses, we can robustly predict the pose of the objects and this different arrangement of the objects. So this is one example of the RGBD sensing for the RSCAR platform, where I'm showing the side view on the top and the top view on the bottom left, and the recomposition that we generate for this scene. And you can see, for example, in this instance, even with the presence of heavy occlusion for the cracker box, we can get a good pose for that cracker box in this example. And these are the results for different arrangement of the scene with the robot in different location, and also the objects in different location with different occlusion patterns. So this is the example of the learned policy for pushing of different objects in to the goal location, and you can see even for different shape of the object, different geometry for bowl and sugar box and banana and the tool, we could be able to push the object within the obstacles and then get that to the goal location. For quantitatively evaluate our system, we used 500 held up test scene to evaluate our method, and we compared with other baseline with the basic RMP and MPC open loop control and direct control. And for evaluation, we use a recall per collision. So if you have a lower collision, higher recall, we are better. So higher bar on left would be better. So we get better results compared to the other baselines. So here I'm showing the comparison of the control for the basic RMP, which is the best baseline that we have, and our method. The baseline is on the left and our proposed method on the right. And you can see that for different scene arrangement, we could be able to move the target object to the goal location without colliding too much with the movable obstacles. Whereas in the baseline, the robot will collide with other objects and move them away, and which is not very good for this task, for example. We also tested this on the real robot, real RC car, and we tested on 32 real scene arrangements. And for evaluation criteria, we used average collision rates, and we tested with the best baseline algorithm that we had in the simulation test. And the baseline produces 65% collision, and our proposed method produces around 18% collision, which is much lower than the baseline. So this is one example of the comparison with the baseline and our proposed method. And you can see that because we have a lookup reward, we could be able to move the target object around the obstacles rather than colliding with the obstacles, and get that to the goal location. And this is another example for other objects with different geometry. And again, for example, in the baseline, because we are not having that sort of a look ahead, we collide with the objects rather than having that kind of a turn motion for the robots. And in summary, we use object level scene recomposition, and we see that as useful for robotic manipulation tasks. And using that, we can deal with complex object arrangement and uncertainty in the scene. And for doing that, we translate the real scene into simulation and use a simulated look ahead reward to evaluate different control policy or control parameter and pick the best one to apply in the real scene. And yeah, this is the end of the talk. If you have any question, I'll be happy to answer.
Are there questions for Hamid? Usama has a question but doesn't want to go first.
I just wanted to give the priority. So Hamid, thank you very much. This is a very, very important and interesting problem. The one thing I wanted to ask you is when we have a robot arm interacting and doing the pushing, and if objects are much larger, then we have interference with the arm. But in your case, you are really doing a planar a problem, dealing with obstacles on a surface, right?
Yeah.
So, I mean, frankly, I would say then if you reduce just take the C space of that and reduce, basically augment the obstacles with the dimension of the object you're moving, the problem is still feasible in 2D. So, what would be really interesting is to see how this can be applied when you have interaction with multiple objects moving through links. So when the arm is really embedded in that space, then it becomes really a more justified problem. I mean, this is maybe the first step in something that very interesting, but we have to see that this is at this stage is limited to a planar problem, right?
Yeah, so I think it's not, actually that's a very good question. So this is not limited to 2D. So in this application, because we are working on non-prehensile manipulation on the planar surface to push object, and we are dealing with like SE2 space. If you want to have like in the 3D, we can use the same control like the RMP, but applying that into 3D. So the difference would be having those control points or not on the 3D space. So we didn't try that in this paper, but one kind of a thing that I can imagine we can try is that if we have, let's say we have this recomposition of the 3D scene in 3D space, actually not on the planar, and then we apply that into the 3D simulation and for the robot environment in simulation. Then we can add that object on other object, for example, that object in hand as a kind of a extra link to the robot. And then when we want to like plan for like a path for different trajectory, then we can do that. So
right. I might comment more when we get to the panel. I really think the problem is, I mean, from the beginning is how to deal with dimensionality, high dimensionality of multi-link systems with interacting with the environment. And that's why so many techniques were developed in randomized motion planning, etc. But we really need to go to the original problem, and I'm glad you see it. I mean, this can go further and being applied to higher dimensional problems. Once you put multiple links, the problem is different, and that is what is challenging. Anyway, thank you.
Yeah, thank you.
Let's thank our speaker again. All right, so now we move to the panel discussion. So if all of the speakers from the previous session could please move to the front if you're here presently, and we're going to bring everyone else who gave a talk onto the screen so we can see you now. All right, so my first question actually has to do with dynamism in planning. So one thing that we saw was that some people were interested in trying to add disturbances into their planners. Other people were saying we were trying to, be more robust to model uncertainties or model changes. Curious, where sensing comes into all of this, if it does, or if this is mostly just something that you think is, it can be solved through more effort on, at least in what your work is doing, on robustifying your planner or your controller. So Let's start with the people, whoever wants to go first, actually. Go for it.
Okay. So in the work that I'm doing, it's on sampling-based motion planning, and we are just taking into account the dynamics of the system. And we are just before doing the motion planning, we are already assuming that the robot will actually follow the trajectories that we have predefined. But in real environments, that's not always the case. So we need to take into account sensing that you said, and incorporate that into the planning, and also take into account maybe dynamic obstacles instead of static obstacles, and take all that into planning, and maybe come up with a better motion planning algorithm that takes dynamic obstacles and also change in trajectories into account while developing the planner.
So that's remarkable, Sharon, because like at least in your planner case, you were very much interested in changing models, and when you're discussing this, essentially you have to branch in a completely different direction for your planner to work with these sorts of...
Yeah, definitely. That would be interesting work to extend.
All right.
My work on.
Cool, thanks.
Yep.
Other thoughts?
So can I?
Please, yeah, go ahead.
Yeah. I think in motion planning is most difficult is actually uncertainty and high dimensional problem is uncertainty and high dimensionality make a problem is very difficult. And we are interested in the kind of the sensor noise because sensor has a lot of uncertainty. So in my case, is for example, from the camera, we have only partial information. That makes very difficult planning. So, in my opinion, I'm also trying to try to a kind of the closed loop vision-based planning. So, for example, we update the sensor information every time steps, and then we update, we change trajectory, or we are trying to do replanning based on the updated sensor information. That is my direction of my research. Yeah.
Thank you. Other thoughts?
Also had a comment on that. So I think perhaps the answer could be both. Like, so in my work, we deal with the uncertainty of the environment in the sensing and also in the motion planning part. So for the sensing, for example, for learning a good recomposition model for like a deep model that we trained, we generated like 1 million samples in the simulation. And using that, we are kind of modeling the noise in the sensing, the occlusion patterns and the clutter that could happen in the real scene with very many different configurations that we have randomly put object in the scene and then sensing and use that for training. So that is kind of related to the sensing part. But for the planning itself, so when we have, for example, for a non-parential manipulation task that we worked on, if you push one object and if the object is colliding with other objects and this object gets away from the path that you planned for, and using that, so if you have even a crude simulation of the physics simulation of the scene, when we apply different policies to the robot and see what happens in the simulation, you have a kind of a better idea of what's going to happen in the real world. Even if it's crude, you can have a sense of like, maybe if the object collides with other object, you can get away from the path that you looked for. And you can use this sort of a closed loop control to kind of correct the policy when the object gets away from the planned path. So that's my thought.
And we saw that very particularly in your work where the other planner was failing because it was running into other objects, and that sort of brought it further away from where it wanted to be in some sense.
Yeah, that is related to that. If the worst case scenario would be, for example, if you have an open planning, you plan for like 50 iteration, but if the object gets collided to the other object in like iteration 10th, then the whole plan gets kind of confused where the object can go after that. So.
Burke has his hand up. Yeah, so Burke, you can go ahead if you like.
Sure, thank you. Yeah, I totally agree in the previous points. I mean, closing the loop in task space is really, really powerful tool that we can have. And even if our models or measurements are somewhat uncertain, There are still powerful tools that we can look into, like disturbance observers, or we can have online adaptive systems that we can work with. But I also want to emphasize here that the mechanics of the system, the mechanical design actually can help us a lot to reduce the uncertainties of the system quite a bit. So if we basically consider this robotic system as a whole, with mechanical design, with control system sensing and everything, all bundled up and designed to fix their weaknesses and basically reduce the uncertainties as much as possible, that I think puts us in a very advantageous position in many cases.
Thank you. Cosmo, did you have something you wanted to add?
Yeah, I mean, first of all, yeah, this point of view that Berk just pointed out, that mechanics. Yeah, when we control guys, we used to not to try to distance ourselves from the mechanics. You have these equations, you have this set of ideal behaviors, and your role is like to force one over the others. But there is really a lot to gain in terms of holistically think to the various things together. So I think it was a great comment. Yeah, if I can add something more on the control side, still I think that most of our advanced nonlinear controllers, we often criticize them because they are not too much model-based, too much prone to errors on the models, but there's actually these other kind of hidden hypotheses that we have this flow of very high frequency and precise information that comes from outside, and that's another thing that it's important to be explicitly taken into account while devising controllers.
Great. Did you have something you wanted to add, Sarah?
I would like to add something because I'm the last one in this session that hasn't said it. But all jokes aside, I feel like there is value in seeing perception, planning, and controls as a holistic, I guess, entity, but also there's value on splitting the three and having more smart people working on very specific problems, assuming that the upstream problems are resolved, and asking the tough questions as well, especially when it comes to like motion planning. I think there is value in assuming that we have this all-knowing, perception of the world too, and solving the critical issues. You have more people working on it.
Excellent point and a great way to end this discussion. And yeah, so Usama.
One last comment.
Oh,
I need a microphone. Yeah. Well, thank you very much. I fully agree. I mean, robotics as a whole is multidisciplinary, and if you are designing an algorithm, you just add one sensor and you change your algorithm. You go and modify a little bit your mechanism, you change the problem. So we really have also to look into that, and I think the more we come closer to understanding, I mean, we don't need to be expert in every area, but we need to at least have that openness to understand what is going on and what can be done, and have those discussions. I wanted really to go back to motion planning. We are putting a lot of effort, smart things taking place. And I think motion planning, let's remember the difficulty of motion planning is essentially in the dimensionality. That is, the configuration space is very high dimensional configuration spaces are difficult to compute, and when we have changes, we cannot recompute them in real time. We came up with the new techniques in the 90s, the randomized motion planning, RRT, and all of these things. And it was really to go over the explicit recomputation of C spaces, C obstacles. Now, if we are in lower dimensional spaces, I think the problem is not that difficult to handle in real time. and the computation power is so strong. So what I really would like to see is how we develop techniques in 2D or lower dimensions, but that extend to higher dimension. This is very, very important to remember. The other thing is with obstacles, you have to remember also that noise and the precision of your sensors is not as critical for obstacles at motion planning as much as it is for dexterous manipulation. So in the case of contact, this is where, this is where we really need the accuracy, because we are touching what stiffnesses with which we are touching, and the characteristic of the surface are very important. But touching an obstacle with a few centimeters or a few inches is not going to change the problem. So that we have also to remember that, and to remember that we really need to deal with the challenges of contact. Contact is very challenging, and if we are planning in free space and in contact space at the same time, well, good luck. Anyway, that was my comment.
Do you want to close us?
Well, you close, and then Bruno and I will close.
This session is closed.
Well,